Okay, so we concluded that the total energy is proportional to the temperature to the fourth power. And so we imagine having a star, and it's the energy at some point on the surface, right, that's being emitted, which is the flux, right? The flux is the energy per unit area. So the flux, therefore, is also proportional to the temperature to the fourth power. And so we can find the total energy generated per unit time, per second, say, which is the luminosity, from the flux, right, by integrating over the entire surface, which is 4 pi times the radius of the star squared. And this must be proportional to temperature to the fourth power, so it's a 4 pi r squared times t to the fourth power. And the only thing that's really missing to make this an equal sign is the right constant. So the luminosity of the star is actually 4 pi times the radius squared, the area, the surface area of the star, times some constant, usually denoted sigma, times t to the fourth. And this is the Stefan Boltzmann relationship. So let's think about using this to determine, say, how large a star is. What is the radius of a star? So let's imagine looking at a fairly at a star in our own Milky Way that we can actually see by eye, and one of these. Let's imagine taking the spectrum. So let's measure or take the spectrum. Right, we see where the spectrum peaks, and we can, as we know from the Planck law, we can identify the temperature. So let's measure the spectrum to get the temperature of the star. And let's say we get that the temperature is 3,500 Kelvin. Okay, so there's this star that we can see by eye that has a spectrum from which we can derive a temperature of 3,500 Kelvin. And we measure, now let's measure the flux. Right, so we measure the radiation from the star, and we get the flux of the star. And we can determine the distance, say using parallax, because it's visible with the naked eye. It's in our galaxy, and let's say that we measure this star is about a couple hundred, 200 parsecs or so. From this, we can get the luminosity, right? So the luminosity is 4 pi times the distance. So this is what we call R in this expression, right? So the luminosity flux relationship. So from the flux and the distance, we get the luminosity. And let's say that we get that it's equal to 1.4 times 10 to the 5 times the luminosity of the sun. Okay? Now we can use this relationship to figure out how big the star must be. So we have L star is 4 pi times the radius of that star squared, sigma times its temperature to the fourth. And for the sun, we have the luminosity of the sun, indicated like that, is 4 pi times the radius of the sun squared times sigma times the temperature of the sun to the fourth. So let's put S here for the star. Oops, sorry. This is the sun, and so we put the symbol for the sun. And so now let's derive, all right, let's divide this by this, and let's get our star over our sun from this relationship. And we'll see that we get, right, we have to take a square root, right, because we get our sun squared divided by our star squared, and we take the square root. And so what do we have on this side? We have the temperature of the sun over the temperature of the star squared times the luminosity of the star over the luminosity of the sun to the 1/2. So let's the temperature of the sun is about, temperature of the surface of the sun is about 6,000 Kelvin, and we said the temperature for this star is 3,500, so it's a cooler star. And so now we know what this is. We can calculate this quantity. We have the luminosity. We have this ratio, right? And so we end up with about approximately a factor of 1,000. So this star is 1,000 times larger in radius than the sun.